Hello. Today, I would like to talk to you about managing carbon emissions across clouds for responsible technologists. My name is Cam Casher, and I'm a senior software engineer at Thoughtworks, and I've been very involved in the green software community, responsible tech community for a few years now, so I'm excited to get to talk to you today. So I'd like to begin this presentation with a bit of a thought-provoking quotation, and I'd like to let this one sit for a second. Personally, I think this is a great segue into the idea of responsible tech, highlighting the idea that we as technologists are responsible, whether the outcome is good, bad, or an unintended consequence. So, not too long ago, ThoughtWorks and the United Nations created a responsible tech playbook together to guide UN teams on their journey of adoption. And I believe that this playbook is an invaluable tool for not only the UN, which contains information, tools, and techniques that are relevant across any organization. So it explores a responsible tech mindset and the tools and techniques that help teams identify strategies to be more inclusive, aware of bias, transparent, and to help mitigate negative unintended consequences. Now, I know we're at the Green IO conference, and the main reason we are gathered together is to discuss sustainable tech, but I wanted to briefly touch on some other topics that we can call out in the playbook, living under the broader domain of responsible tech, since in a lot of ways, these are equally as important to sustainability. So the following topics are data and AI, focusing on the emergence of generative AI tooling and combating misinformation with responsible AI, privacy, focusing on improper data processing, storage, or transmission, understanding that privacy is a basic human right, security, focusing on protecting data, resources, and reputation, as well as the best practices for dealing with more sensitive information. We have inclusive design and accessibility. So accessibility was originally intended to design products and places for with a focus on people with disabilities. And now accessibility focuses on identifying exclusion and learning from diversity and extending solutions to all. Then we have DEI, or diversity, equity, and inclusion, which helps us to incorporate varied perspectives and lived experiences, which in turn helps us better be able to solve for the needs of our users and create positive social change. And lastly, which I'll bring the focus here today, we have sustainability, which explores the areas of sustainable tech and with a deep dive on creating tech that has a lower environmental impact over time. So, I wanted to, show you a glimpse of the responsible tech playbook here. I know this is a very text-heavy slide, so just know that this is just a sample. But the reason I wanted to talk about the responsible tech playbook is to give you a glimpse at the section on sustainability. So, um, I think it's important to touch on this because it gives us an introduction to the concept of green ops. And I want to directly read off the definition here to have a base level understanding for everybody. So, green ops is a cultural practice that enables organizations to consider and optimize for carbon and energy as key metrics for data driven decisions in technology and operations. By adopting a green ops approach, organizations can optimize not only for their carbon footprint, but also can reduce costs, grow their capabilities, and sustain carbon driven work. And this approach will consider carbon and energy as cross functional requirements throughout the development process. So, next, I want to talk about a more practical example of how we've applied green ops at ThoughtWorks. And the basis of our approach revolves around the green software fundamentals phases identified by the Green Software Foundation, or the GSF, of learn, measure, and reduce. And these phases include understanding the emissions drivers and their relationships to each other, measuring and accessing the right data, and implementing the necessary optimization strategies to reduce an organization's carbon footprint. And To make sense of emissions metrics and why certain cloud services may be more or less carbon intensive, it's important to have a fundamental understanding of green software principles, emissions drivers, and the broad domain of sustainability in tech. And principles might range from carbon efficiency to energy proportionality. These are essential for engineers to understand when looking to optimize their cloud infrastructure. And then after obtaining access to real-time data and enabling visualizations for monitoring, the natural next step for us was to more deeply analyze spikes and trends and ultimately identify opportunities to implement strategies to mitigate emissions and lower costs. And through sufficient analysis, Thoughtworks teams were able to consider ways to reduce their cloud carbon footprint and identify remediation strategies that would be most fitting for their objectives, requirements, or infrastructure needs. So to calculate the total software carbon emissions, you need to access detailed data regarding the energy consumption, carbon intensity, and hardware that your software is running on. And this is challenging data to gather. Luckily for us, at the time, I was heavily involved in maintaining the open source tool Cloud Carbon Footprint. Unfortunately, due to changing business conditions, Thoughtworks hasn't been able to invest in the continued support of the tool in recent months. I do understand the impact this has on users and adopters, which is obviously less than ideal, but I've also been informed that Thoughtworks has an existing effort to have CCF better maintained in the near future. And I also know that support from the community would go a long way for anyone who's willing to help champion its success. So for our use case, we revolve specifically around the use of CCF for our carbon data capture. And the nature of CCF's methodology focuses on calculations based on billing data and summing up resource usage totals. But it's important to call out that totals don't always tell the whole story. So imagine a growing company that's measuring their cloud carbon footprint. As they scale, their totals will likely continue to increase, which doesn't always give you the best perspective on the effectiveness of green software practices. So this is where the software carbon intensity standard comes into play. The SCI is about calculating the rate of emissions. So in automotive terms, this SCI is more like miles per gallon measurement, where CCF, for example, might be more like total carbon footprint of a car manufacturer and all the cars they produce every year. And I'm not going to dive into this calculation, but would highly suggest learning about it if you're interested. And then another open source tool that I've come across, which may excel in the measurement of more compute extensive applications, like those running Gen AI tools or LLMs, is a tool called Code Carbon, which tracks the energy usage of code during execution. So, there are a few other ways or a few other reasons why using CCF for our carbon data made sense at the time. One of those being that the calculation methodology was able to be cloud agnostic. So in the case of ThoughtWorks, we're looking to understand operational emissions associated with multiple cloud providers like AWS and Google Cloud Services. And I wanted to take a second to get a high level understanding of how operational emissions are calculated. So this is the energy consumed while your cloud services are actively running. And we calculate it by first taking the cloud provider's usage data, and then we convert that into kilowatt hours using energy conversion factors. So considering a compute resource, for example, we can derive an estimation for total watt hours by understanding average watts and also resource running time and the estimated number of vCPUs. Average wattage information can be estimated by understanding the underlying hardware associated with your compute resources and utilizing publicly available data sets to find min and max watt information, for example, as well as the average CPU utilization. Estimating storage and networking resources would have slightly different calculations. So then we multiply that number by the power usage effectiveness, or PUE. And PUE is a measure of how efficiently a data center uses its power. So for reference, A PUE of 1.0 means all the energy in a data center is used for computing, which in reality, we know that's not the case because there's always some overhead for cooling or other infrastructure. And finally, we have we multiply by the grid emissions factor. So this is crucial because the carbon footprint of a kilowatt hour of electricity varies dramatically depending on where it's generated. So a data center powered by renewable energy will have a much lower grid emissions factor than one powered by fossil fuels. So typically the information can be found on the cloud service provider website for where the data centers are located. You could also consider using tools like electricity maps to get real time and hourly grid emissions data. But yeah, this is how you calculate operational emissions. And now I want to just touch briefly on the whole calculation of total CO2e. So when we're considering everything, we also want to take in operational emissions plus embodied emissions, which can often be overlooked. But essentially, it's the carbon footprint associated with the manufacturing of the servers themselves. And building servers requires energy and materials, and that contributes to the overall emissions. So the CCF methodology also covers on ways to estimate this using publicly available data sets, but I'm also not going to dive into this for now. But the important things to take away from this overall methodology, I would say, are understanding with CPU utilization, servers don't use energy in a linear way. Even when they're idle, they're still consuming power. So it's not just about how you use them, but how efficiently you use them. Considering the different resource types like compute, storage, and networking, those all have different energy profiles, so different calculations. We rely on data from cloud providers themselves to get accurate usage information, but also publicly available data is imperative for these calculations. And lastly, as I mentioned, where your data center is located has a huge impact on the overall carbon footprint. So by understanding all these factors, you'll get a clearer picture of the environmental impact of your cloud usage and be able to make more informed decisions on how to reduce it. So now let's understand how we're able to use the CCF data and create meaningful insights. So we use several Google Cloud services to pipeline and visualize our carbon emissions data, and these include Cloud Scheduler, which is a cron-like service that allows you to schedule jobs to run on a recurring basis. We use Cloud Scheduler to schedule a job to run every day at midnight, and this job triggers a PubSub message. So PubSub, which is a messaging service that allows you to send and receive messages between applications. We use PubSub to send the message from Cloud Scheduler to a Cloud Function. So Cloud Functions is a serverless platform that makes it easy to run code without having to provision or manage servers and has scale to zero feature to help mitigate cost. And we use Cloud Functions to automate the daily requests that are used to collect our carbon emissions data for Google Cloud and AWS specifically. Then we have App Engine, which is a fully managed platform that makes it easy to deploy and scale web applications. And we use App Engine to run our CCF application itself. Then we have BigQuery, which is a serverless, highly scalable data warehouse that makes it easy to store and analyze large amounts of data. We use BigQuery to store our carbon emissions data. And lastly, we have Looker Studio, which is a business intelligence platform that makes it easy to create interactive dashboards and reports. And this is where we're visualizing our carbon emissions data. So the entire flow is Cloud Scheduler triggers a PubSub message daily. That message is consumed by a Cloud function that hits the CCF API with a query for just 1 day's worth of data. This function pushes the data upstream, appending it to a BigQuery table. That table is then consumed by Looker Studio and joined with billing export data for many data visualizations. So now let's take a look at an example. And in the following chart, we can see there's 3 usage spikes and 4 emissions spikes. So We can conclude a few things from this. First, the cost of usage is not a perfect proxy for emissions. There's a big spike in emissions in early March, which you can see, with no corresponding rising costs. And there can be a number of reasons for this, including potential use of cloud savings plans or other billing cadences for reserved instances. And second, we really know that we should dive in and understand what happened in February and March. So, in fact, we did do this, and we were able to take steps to resolve the spike. So, looking at the chart shows us here emissions by cloud service over time. And in this chart, we're narrowing the scope to March 4th through March 12th, which is where we saw that big spike on the last slide. So this gives us this view, and this is we can see from the table below that the product contributing most of our emissions bulge is Cloud Composer by a significant margin. And looking a bit deeper, we can see that only 3 Google Cloud projects are contributing about 90% of this spike. So with this information now in hand, we're able to reach out to the teams responsible for these projects in real time and work with them to discuss remediation strategies. So then looking at the situation 4 weeks later, we can actually find a much narrower gap between Cloud Composer and Compute Engine. The estimated emissions from the use of Composer have been reduced substantially. So how did the teams achieve this? Well, it was a combination of right-sizing their environment size to reduce inefficiencies and lowering the auto-scaling configurations to use less workers, less slotted virtual CPUs, memory, and storage. And moving forward, there are a number of existing resources that not only cloud practitioners, but general technologists can use to help identify proven patterns to achieve carbon optimization and reduction. So, this all stems back to learning, measuring, and reducing, which was the green ops cycle. And it can be really a recurring cycle for teams to stay knowledgeable and take action in real time. And the beauty of working with green ops in ways like this is the opportunities are really endless. And you could really consider automating alerts, for example, if the carbon thresholds reach above certain levels. Or you could make these charts readily available for every team and decentralize the ownership, letting each team have their own accountability for resource usage, which really can tie into FinOps best practices as well. So to wrap up here, I wanted to call out the hot topic of addressing carbon emissions and generative AI and how most companies are realizing measuring it can be extremely challenging. So we know that emissions from Gen AI are associated with both the development phase of training AI models and the operational phase of using the AI models. And to effectively tackle this issue, transparency is key. We need mechanisms to track and report emissions data, which will empower organizations and users to make informed decisions and incorporate AI's environmental impact to broader sustainability efforts. And optimizing AI models for energy efficiency will only become more important. And this involves considering factors like the model's complexity, its architecture, like the hardware it runs on, and the energy sources powering that hardware. And additionally, the emerging practice of green prompt engineering focuses on crafting prompts in a way that minimizes computational resources required to generate a response, thereby reducing energy consumption. So with that, I'd like to say thank you. I wanted to give you an idea how to maybe start up a grassroots program at your organization and really just provide transparency to how cloud usage can be managed and understood with carbon emissions. So thank you very much. Here's a link to the playbook if you're interested, and have a nice day.